Hello everyone and welcome to the lecture today. Today we'll be talking about relation operations, so some more complicated relation operations, representations, so how to represent a relation using mathematical objects, certain ways of doing this, and we'll be talking about how to define and use equivalence relations. So let's start by defining a very important operation called the composition relation. The composition of two relations. So we'll let R be a relation from set A to set B, and S be a relation from set B to set C. The composite relation or the composition of R and S is a new relation from A to C that consists of all ordered pairs A comma C where A is in A, C is in C, and there exists an element B in B such that A is related to B under the R relation, and B is related to C in the S relation. And in terms of notation, we use a very similar notation to our function notation from before for composition of functions. Is going to be S composed with R. This is the notation that we're going to be using to denote the composition of two relations. Just for a very simple example, consider the set A to be 1, 2, 3, B to be the set 1, 2, 4, or 3, 4, and C to be the set 0, 1, 2. And now consider the relation R to be 1, 1, 1, 4, 2, 3, 3 comma 1, and 3 comma 4, and consider the relation S to be 1 comma 0, 2 comma 0, 3 comma 1, 3 comma 2, and 4 comma 1. In which case S composed with R is going to be 1 comma 0, 1 comma 1, 2 comma 1, 2 comma 2, 3 comma 0, and 3 comma 1. And this is because 1 comma 1 is an R, 1 comma 0 is an S, therefore 1 comma 0 is going to be an S composed with R. And you may be wondering why 1 comma 1 is showing up in this composition, but you can see very clearly that 1 comma 4 is in the relation R, and 4 comma 1 is in the relation S. So 4 is connected to the second component of R, or of this element right here, to this first component of this ordered pair. Therefore 1 comma 1 is in this composition relation, as is the same for each one of these, and only each one of these values right here. So it might be a little bit easier to see if we sort of draw a diagram here illustrating this fact. So we kind of draw each of our sets out. 1, 2, 3. This is A. We draw 1, 2, 3, 4, which is our B. Then we draw 0, 1, 2. And in R, we have that 1 comma 1 and 1 comma 4 are in the relation. 2 comma 3 is in the relation. 3 comma 1 is in the relation, and 3 comma 4 is in the relation. And then for S, 1 comma 0 is in the relation, 2 comma 0 is in the relation, 3 comma 1 is in the relation, 3 comma 2 is in the relation, and 4 comma 1 is in the relation. And this more clearly kind of shows you why all of these elements are in the relation. 1 comma 0 is in the relation because we can find a direct path through B into C through elements that are in the original two relations. So you think R goes from here to here, S goes from here to here, S composed with R goes from A to C, and it's all straight connected paths. We have 1 right here, 2, this is 2 comma 1, which is this element right here, 2 comma 2, which is this element right here, 1 comma 1, this element right here, 3 comma 1, then lastly 3 comma 0. But we clearly can see from this picture, this figure, what is meant by the composition of two relations. And hopefully you can clearly see that these relations are very, very closely related to this idea of information flow, and are a central tool in modeling information flow in networks in certain types of systems. Specifically, we're going to see that relations are directly related to graphs, mathematical graphs, not the graphs of functions, but to what's called a mathematical graph, which is sort of like a network. And graph theory is a huge theory that's very important in all sorts of studies of information flow and networks, and many other very important examples. So we'll start by kind of simplifying this idea a little bit more. So let's move on to see how this simplifies when we consider a relation from a set into itself. And this is related to what we talked about last lecture. All of those relation properties are for relations on just one set A. So let R be a relation on a set A, or a subset of A cross itself. The powers of a relation are denoted R to the n for n equals 1, 2, 3, any positive integer, and are defined recursively by R to the 1 is just equal to R, and R to the n plus 1 is equal to the composition of R to the n with itself. Now, this definition clearly shows then that R squared is R composed with itself, R cubed is R composed with R, and so on and so forth. Because this is just R squared composed with R. And the idea here is that we're going to see this is very, very closely related to this idea of composition, has a very intimate connection with the transitivity property that we talked about before. So we'll just consider a very quick example first. So that'll be the relation 1, 1, 2, 1, 3, 2, and 4, 2, or 4, 3. If we go through and use a similar idea to what we did before, we consider looking for R squared. Well, we end up getting the 1, 1, 2, 1, 3, 1, and 4, 2. R and R squared. It's just R composed with itself, because 1 comma 1 is an R, 1 comma 1 is an R, therefore 1 comma 1 is in the final relation. There's no other elements that start with 1, so there's no other elements coming from this guy right here. 2 comma 1 is an R, and 1 comma 1 is an R, so therefore because 2 comma 1 and 1 comma 1, 2 comma 1 is in this set, 1 comma 1 is in this set, we can kind of connect this element to 1 comma 1 to get 2 comma 1. 3 comma 2 is in this set, and 2 comma 1 is in this set, therefore 3 comma 1 is in this final relation. Then lastly, 4 comma 3 is in this relation, and 3 comma 2 is in this relation, so we get 4 comma 2 right here. If we do this again, for R cubed, where we take R squared, compose it with R, you end up getting 1 comma 1, 2 comma 1, 3 comma 1, and then lastly 4 comma 1. And additional computation shows that Rn equals R cubed for all n greater than 3. So R4 equals R cubed for this example, R5 equals R cubed, and so on and so forth. And you can go through and verify this. It's definitely good to go through and verify. It'd be a good exercise for you to go through and check. However, what's really neat here is we are seeing directly here that this is giving us a way to connect to transitivity of the original relation, because the original relation is as given is not transitive, but there's a very deep connection to the transitivity property here in this series of compositions that we're creating. And this connection can clearly be seen when we consider the transitivity of R. Right? R is not transitive. Take, for instance, the element 3 is related to 2, and 2 is related to 1, but 3 is not related to 1 under this relation R. However, what we can do is we can form a new set, R star, which is the union of R with R squared, R cubed, and then because every power after R cubed is the same, the union of the powers of R will give us this new set, which is 1 comma 1, 2 comma 1, 3 comma 2, 4 comma 3, 3 comma 1, 4 comma 2, and then lastly 4 comma 1. This is the union of these three sets. And this union now, this new set, which is larger than the original set, is in fact a transitive relation. You can go through and check that. And this is a really big idea, because what this means is that given a relation that doesn't necessarily have one of the properties that we talked about before, we're going to be able to close it and sort of give it that property by adding certain elements back into the relation, which is really neat, very neat idea. And I guess we have one big theorem here that I want to go over, and it's related to this. So the relation R on a set A is transitive if and only if the nth power of the relation is a subset of R for all n in the positive integers. So every power is contained inside the relation itself. And to prove this, we have to split it up into two parts. And the proof of this is very clever. We're going to start with the if part. So we're going to show that if R to the n for all n is a subset of R, then the relation R is transitive. So I'm going to assume that Rn, the nth power of the relation, is a subset which means that if A comma C is an element of R squared, for instance, then A comma C is also an element of R. So we're going to take some element A comma C in R squared. By definition of the composition, there exists an element B in A such that A comma B is in the relation and A comma C or B comma C is in the relation. And this is by definition of the composition, the set R squared. Therefore, R is transitive. So this completes the first part of the proof. The second part of the proof, the backwards part, is the part where we actually do use this assumption for all n in Z+, and it's actually proved by induction. So what we do is we say we're going to assume that the relation R is transitive. If it is transitive, then what we're going to try and do is show by induction that R to the n must be a subset of R. So in order to do this, we'll start with our base case. r to the 1 is by definition equal to r, which means it's trivially a subset of R. And R squared is a subset of R by definition of transitivity. The definition of transitivity means that there exists an element that connects two arbitrary elements in a given relation. So then the inductive hypothesis is that there exists some k in the positive integers such that r to the k is a subset of R, the inductive step is to show that for all k if r to the k is a subset of R, then r to the k plus 1 is a subset of R. And now this is a pretty neat proof here. What we're going to do is we're going to assume that r to the k is a subset of R. This is our inductive hypothesis. And then we want to show r to the k plus 1 is a subset of R. So what we have to do is take some arbitrary element, a comma b, in r to the k plus 1. If we can show this arbitrary element a comma b is also an element of R using this assumption, then we're done. We know that r to the k plus 1 is just r to the k composed with R. So we take this AB in r to the k plus 1, and by definition, this is the definition of composition that we talked about before, there exists some element x in A such that A comma x is an element of R, and x comma b is an element of r to the k plus 1, or r to the k. And by our inductive assumption, r to the k is a subset of R. So a comma x is an element of R, and x comma b is an element of R. And lastly, then, by the assumption of transitivity, then we have that a comma b must be an element of R. And therefore, rk plus 1 is a subset of R. Which finishes the proof here, because we've gone both ways. And we now see the way forward towards computing what's called the transitive closure of a given relation. So before we talk about that, I want to kind of switch gears a little bit and talk about some very interesting applications towards linear algebra. And I shouldn't say just applications, because it's kind of connections with relation properties. We have this very interesting connection between relation properties and matrices. And I guess before we get into that, I have to first define what a matrix is and how to kind of do very special operations with matrices related to what we're doing right now. So a matrix is a rectangular array of numbers. A matrix with m rows and n columns is called an m by n matrix. The plural of matrix is matrices, and a matrix with the same number of rows as columns is called square. Two matrices are equal if they have the same number of rows and the same number of columns, and the corresponding entries in every position are equal. And for notational purposes, we can always write down any matrix as follows. This is A11, A12, and so on and so forth, all the way to A1n, A21, A22, A2n, is AMN, AM1, AM2. So this is notationally how we're going to be talking about the always writing down any given matrix. But we say the ith row of A is the matrix. The 1 by n matrix. AI1 to AIN. And the jth column of A is an m by 1 matrix consisting of A1j, A2j, and so on and so forth, all the way to AMJ. And we have some very special examples. The identity matrix is defined as I if we know what n is, but if we don't know what n is, this is a square matrix that has ones along the diagonal. Is a very special matrix. So it's just ones along the diagonal. This is called the identity matrix. Super important in linear algebra and in a number of different applications, but this is just one very very important matrix. You could also talk about the n by n zero matrix. This is just a matrix with zeros everywhere. And there are many different other special examples that you can come up with. But we sometimes say that the identity matrix, right, is the same thing as what's called the Chronicle delta function, which is a function of I and j, where it's 1 if I is equal to j, and 0 if I is not equal to j. And this is related to that the membership function that I talked about before, right? It's only ones along the diagonal when you have the same row as you do column. There are many different matrix operations that we can introduce. However, the first operation is the sum. So to write this out nicely, we can say let A equal Aij and B equal Bij. The sum matrix of A and B is the component-wise sum of A and B. So the sum matrix is noted by A plus B and this is going to be the new matrix whose ijth component is Aij plus Bij. Important to note that the sum is only defined and makes sense if A and B are both m by n matrices. So they have to have the same dimensions. M does not have to be equal to n. They don't have to be square, which is important, right? You can sum arbitrary size matrices, but they both have to have the same size in order for the sum to be defined. So just for example, if A is 2, 3, 1, 0, and we talk about doing A plus I2, this is going to be the matrix 3, 3, 1, 1. Because remember, I2 is the matrix 1, 0, 0, 1. So the next operation that I want to define is what's called scalar multiplication. And the idea here is that if A is a number, we say that A times the matrix A is just, I'll use this a little bit, use S for our number just to make things a little bit nicer. S times the matrix A is the same thing as S times A11, S times A12, S times A2, 1, S times A2, 2, and so on and so forth. And so on and so forth. So the idea here is that scalar multiplication with the matrix A is just the component-wise multiplication of a scalar, or a number from the field of numbers that the matrix is coming from. These multiplications need to be defined. So, like for instance, if we talk about A being the matrix 1, 2, 3, 4, 2 times A is going to be 2, 4, 6, 8. Which is really just what we need to talk about scalar multiplication. So this should be clear and make a lot of sense. In terms of matrix times a matrix product, things become a little bit more complicated. We actually have multiple different types of valid multiplications that we can define. And this is why things are a little bit tricky. For instance, if you ever use MATLAB or a similar computational software, very often if you type the multiplication symbol between two matrices, you do not get the correct matrix product. You get something that's called the Hadamard product, or the Hadamard product. And this is something that is the following. We'll denote it by A circle B. Note, this is not related to composition, so be very, very careful. But this is a very common notation for the Hadamard product. There are other ones, but this one is very common. And this is the matrix Aij times Bij. So the component-wise sum of the products of the matrix. And this is the definition here. So for example, if A is 2, 3, 1, 4, B is 3, 1, 2, 4, then the Hadamard product of the two matrices will be 6, 3, 2, 16. Right? This is not what people normally mean when they talk about the matrix product. But that being said, this is a type of matrix product, and you can study the properties of it. Another important matrix product that pops up in applications is called the Chronicle product. this is related to what's called the tensor product. And I guess I want to make a note here. For the Hadamard product, A and B must be m by n. They must have the same dimensions in order for it to be defined and make sense. For the Chronicle product, you can define this for generally, so A is an m by n matrix, and B is a p by q matrix. The Chronicle product is defined, well, it's denoted as A circle cross B and we kind of pull in the definition of a scalar multiplication here. We say that this is now a new matrix that's we can kind of express as what's called a block matrix. So we take all of A and do the scalar product A11 times the matrix B, A12 times the matrix B, so on and so forth, all the way to A1n times B, A M1 times B, A M2 times B, all the way down to A Mn times B. And then lastly we write in the matrix B multiplied by each one of these A11s. So it's kind of like the scalar product of each component of A with B arranged into matrix form. This is a new matrix that's much larger than the original matrix. And its size is going to be P times M by Q times N. So for example, if A is the matrix from the previous example, 2, 3, 1, 4, and 3, 1, 2, 4, the Chronicle product is going to be 2 times B, 3 times B, 1 times B, and 4 times B. Which is going to be 6, 2, 9, 3, 4, 8, 6, 12, 3, 1, 12, 4, and 2, 4, 8, 16. So this is very neat, and it's very useful in many areas of mathematics and physics. But the main thing that we're going to define today and we're going to use with our relations is what's colloquially known as just the matrix product. So much so that we're not even going to give it a specific name. We're just going to call it the matrix product. And typically when you see two matrices next to one another, this is the product that's talked about or meant. If you have a matrix A and a matrix B and you see A, B, or A times B, this is what's being talked about. So we're going to let A, B, and M by K matrix and B, BA, K by N matrix. The product of A and B is noted by A next to B is an M by N matrix with its ijth entry equal to the sum of products of the ith row of A and the jth column of B. And the formula for if C is equal to A times B, the formula for Cij is equal to the summation from K, or I equals 1, L equals 1 to K, of A, I, L, B, L, J. Or in the book, it's just kind of written out as A, I1, B1J, A, I2, B2J, and so on and so forth, all the way up to A, I, K, B, K, J. So this gives us our definition here, and we can very clearly see right, how this is proceeding. And we got a nice figure that we can take a look at, just kind of describing this process. This idea right here. I'll make this a little bit bigger so you can see it. The idea here is that if we have a matrix A times a matrix B is equal to C, the ijth entry in C is the ith row of A multiplied by the jth row of B, and all of these entries added together. So this is a very, very good good description of how to go through and multiply two matrices. Now let's see this for some examples, because we really want to understand in depth this matrix multiplication when we go and define our application to relations. So, for example, if A is equal to 1, 0, 4, 2, 1, 1, 3, 1, 0, and 0, 2, 2, and B is equal to 2, 4, 1, 1, 3, 0, this is going to be 4 by 3 matrix. B is a 3 by 2 matrix. So A times B is going to be a 4 by 2 matrix. And specifically, it's going to be the matrix 14, 4, 8, 9, 7, 13, and 8, 2. And you may wonder where some of these values come from. Let's just go through what we call this C. We'll use the formula to kind of check a couple of these. So let's look at C21. C21 is going to be the second row multiplied by the first column, added together. That's going to be 2 times 2, which is 4, plus 1 times 1, which is 1, plus 1 times 3, which is 3, which is going to be 8. So that matches up very nicely. C2 is going to be 2 times 4, which is 8, plus 1 times 1, which is 1, plus 1 times 0, 0. That's 9. So this is a good example. We note that we have exactly that. An M by K matrix by a K by N matrix gives us an M by N matrix, in this case 4 by 2. We do have that matrix multiplication is associative, meaning that it's relatively straightforward to go through and prove. And there are many properties that hold, but you can prove that A times B times C is the same thing as A times B times C. And there are many other properties, but this is just one of the big ones that we use when proving things. However, it is not commutative, right? Which means that A times B in general is not the same thing as B times C. Right? Because if you take A and B here and try and do B times A, the matrix multiplication is not going to make sense, because you can't do it, multiply a 3 by 2 matrix by a 4 by 3 matrix. But even if the matrices are square matrices, for example, the matrix A is 1, 1, 2, 1, and the matrix B is 2, 1, 1, 1. If you go through and do A times B, this ends up becoming 3, 2, 5, 3. But B times A is 4, 3, 5, 2, which is not the same. So these are not equal to one another. And what this means, right, is that we have to be very, very careful in general when introducing new mathematical structures, because they don't always behave like older mathematical structures. And sets of matrices are very, very rich in terms of their mathematical theory and how we understand them. But the idea here is that they're going to be very, very important to us now in terms of better understanding relations. In actually describing relations. So we have one more matrix operation that we can define. It's going to be really important. This is the transpose. Is the n by m matrix obtained by interchanging the rows and columns. of A. And just for a quick example here, if A is the matrix 1, 2, 3, 4, 5, 6, then A transpose is going to be 1, 2, 3, 4, 5, 6. So it's going to be, this is a 2 by 3 matrix, 3 by 2 matrix. The notation for the transpose is AT. This is how we denote the transpose. And you also have a characterization of symmetry of a matrix. If the transpose is equal to the matrix itself, the matrix is called symmetric. So a square matrix A is called symmetric if A is equal to the transpose of A. Means the off-diagonal components are equal to one another. So this brings us to a very special example, a very special type of matrices. A matrix is said to be a 0, 1 matrix if its entries consist of either 0 or 1 and no other number. 0-1 matrices are often used to represent discrete structures, such as graphs and networks. Algorithms that are use these structures are based on Boolean arithmetic with 0-1 matrices. So the idea here is that these objects are very important. The arithmetic between 0-1 matrices is based on Boolean operations and an OR. Right? So we're going to see a very neat connection between what we've been talking about so far and discrete structures. For two matrices that are 0-1 matrices, I'm going to have let A matrix Aij and B matrix Bij. So both of these be M by N 0-1 matrices. The join of A and B is the 0-1 matrix with ijth entry Aij or Bij. So you can think about it like it's like the Hadamard product like before, but instead this is just the OR operation done between each and every element in the matrix. Correspondingly, the meet of A and B is the 0, 1 matrix with the ijth entry given by Aij and Bij. This join can also just be denoted as A or B. And likewise, the meet can be described as A and B. For example, if A is 1, 0, 1, 0, 1, 0, and B is 0, 1, 0, 1, 1, 0, A or B, the join of A and B, is going to be 1 or 0, which is 1, 0 or 1, which is 1, 1 or 0, which is 1, 0 or 1, 1 or 1 is 1, 1, 0 or 0. And the meet, A and B, is given by 1 and 0, which is 0, 0 and 1, which is 0, 1 and 0, which is 0, 0 and 1, which is 0, 1 and 1, which is 1, and 0 and 0, which is 0. Oh, and this should be the and symbol here. And just like we can kind of generalize a couple of our operations now to these 0, 1 matrices, right? We can also extend our operation of matrix multiplication. If A is an M by K 0, 1 matrix, and B is a K by N 0, 1 matrix, the Boolean product of A and B, denoted as A circle dot B, is the M by N matrix with ijth entry if A Boolean product B is equal to some matrix C, then Cij is equal to the OR operation L equals 1 to K of the AND operation between the ith row of A and the jth column of B, which can be written out directly in terms of AI1 and B1J, or AI2 and B2J, or so on and so forth, all the way to AIK and BKJ. Now, if you look at this and you really kind of think about what this is telling you, where this formula is coming from, it's exactly the same as the formula for normal matrix multiplication, but with the sum replaced with the OR operation and the multiplication replaced with the AND operation. Right, so this is really kind of the nice way of kind of thinking about this. And when you go through and use this, right, it's relatively straightforward to go through and use. And we're going to see this as a really, really close, it's a very, very important analogy in understanding the closures of an equivalence, or the closures of a relation with respect to transitivity. We'll just see an example of doing this product. If A is 1 0 0 1 1 0 and B is 1 1 0 0 1 1, then the Boolean product of this matrix, and I didn't write it out directly for the normal product, but I'll probably do this just to kind of show you. It's 1 and 1, this and this, or 0 and 0. The next entry is going to be 1 and 1, 1 and 1, or 0 and 1 and 0, or 0 and 1, 0 and 1, so we're in our second row now, or 1 and 1, or 1 and 0, sorry, 0 and 1, or 1 and 0, 0 and 1, or 1 and 1, 0 and 0, or 1 and 1, 1 and 1, or 0 and 0, 1 and 1, or 0 and 1. And lastly, 1 and 0, or 0 and 1. And this is going to be 1, this is going to be 1, this is going to be 0 because each of these is false, this is going to be 0, This is going to be 1. 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 And the last one, this is going to be 0. This new matrix is the Boolean product of these two matrices. And this is a very, very kind of interesting idea, which is going to be extremely fruitful in terms of better understanding relations between finite sets.